All right, this is officially our last concept review for the AP exam. It's on torque and rotational motion. So let's start with the definition of torque. So torque is sort of the rotational equivalent of force. And it's calculated if we have some object, right, and we have some point that is a rotation axis. So let's say the object is fixed to rotate about this point. If this point right here, right, if we exert a force on that object, the torque from that force can be found by taking the moment arm, right, that's the distance from the rotation axis to the point where the force acts, and multiplying it by the perpendicular component of that force. We could write it like this, for example. This would be another way of writing it. To find the direction of torque, we actually use the right-hand rule. So in this example here, this thing would want to rotate clockwise, but we can use the right-hand rule to define the vector direction of this torque because torque is a vector. So if we did use that right-hand rule, if you curl your finger in the clockwise direction, to do that you have to point your thumb into the page. So the vector direction of torque would be into the page as given by the right-hand rule. And just to make it really clear, this force, this component here, right, that I just sketched in, maybe I'll make this a little small, right, that is F perpendicular, right there. Okay, so one of the situations that we studied torque was torque statics. So this is when objects are at rest, but you've got multiple forces acting on objects in different directions, for example. So in the case of a torque statics question, well, the net torque on that object and the net force on that object have to be zero. And you can use these static equations to build and combine sets of equations to solve for things that you want to solve for. So here's an example. So let's say we have some sort of a rod, and we are told that this rod is in equilibrium. So it's static. It's not accelerating linearly or angularly. Well, there's two forces up, there's one force down, and it's told us some of the distances. Now, things we know that the net force on this has to be zero. So the magnitude of F1 and F2 should sum to F3. We also know the net torque on this has to be zero. And in order to use this to build an equation, well, the first thing we have to do is we have to choose a rotation axis. So I'm just going to go ahead and choose to put our rotation axis at F1. If we do that, this force will exert no torque because there's no moment arm distance to this force from this point. So that means that the torque caused by F3, rotating it this way, right, so that's an into the page torque, should be balanced with the torque caused by F2, which is trying to make it rotate that way. So the net torque equals zero equation would simplify to look like this. If we made this the rotation axis. If we put the rotation axis somewhere different, we'll have a different equation. But it's really, you can put it wherever you want. Whatever equation you derive will be valid. Now, rotational kinematics. This is just like regular kinematics, but we've got rotational versions of the quantities plugged into the equations. So this is just the equation for average velocity, but this is angular velocity, and instead of displacement, we have angular displacement. Similarly, for average acceleration, instead of translational linear velocity here, we have change in angular velocity per time. Now, these are just some of the kinematics equations with the angular quantities plugged in. Notice that they're just like the linear kinematics equations, just with the angular quantities instead of the linear quantities. One of the main things we talked about also was Newton's second law for rotation. So this is the rotational equivalent of net force equals ma. Instead of force, we've got net torque. And instead of mass, we've got rotational inertia, right? So this is a lot like inertial mass, but it's in the case of a rotating object. And here, this is the angular acceleration of the object. So in this example here, we've got some circular object. Let's say it's mounted about an axle here in the center, like right there. And we've got two forces pulling on it, right? One force directed this way, another force directed this way. Well, if we want to find the angular acceleration of this object, we can use this to set up an equation. We would have one torque caused by this force, and that would be in the counterclockwise direction, out of the page. And we would have another torque caused by F2 into the page. So if I call out of the page direction positive or counterclockwise positive, the net torque would look like this, right? So this would be the net torque on that object, and that would be equal to its rotational inertia multiplied by its angular acceleration. Now, to talk about what rotational inertia really means, well, it's like inertial mass, but it has to do, it is for objects that rotate instead of objects that are moving with translational velocities and accelerations. So what it really gives is an object's tendency to resist angular acceleration. And it depends on two attributes of the object. One is the total mass, so how heavy is it? And secondly, how far is that mass concentrated away from the rotation axis? So if we had an object like this, right, if you were to make these heavier, that would make its rotational inertia get larger. But if you also made it longer, that would make its rotational inertia larger as well. Now, in the case of just point particles, right, so if we were ignoring the mass of this rod, we could find its rotational inertia by using this equation. Right? Take each mass and multiply that mass value by its distance from the rotation axis squared. And we would sum this value for all of the masses that are part of the object. In the case of symmetric objects, there are actually equations that give you their rotational inertia. And notice that these equations depend on the mass of the object and the size of the object, right, the radius, squared in every situation. But there's a different fraction. And the value of that fraction depends on overall, is that mass concentrated far away from the center, or is that mass concentrated closer to the center? So in the case of the ring, for example, the mass is all at the very edge. So the fraction there is 1. But in the case of the disk, right, the mass, some of the mass is concentrated close to the center, some of it's concentrated far away. So it's going to have a smaller rotation overall, or a smaller rotational inertia overall. And that's why there's a 1/2 fraction here. And depending on what the shape is, those fractions will be different because the concentrations of mass are different throughout those objects. Angular momentum. So this is the equation for angular momentum. It looks a lot like the linear momentum equation, which is this. It's just the angular version of that equation, right? So we've got angular momentum, rotational inertia instead of mass, and angular velocity instead of translational velocity. The reason this is important is because it is a conserved quantity if you have a closed system, which means that if we have a closed system, the initial angular momentum of that system will equal the final angular momentum of that system. After a collision or interaction between objects inside that system, the momentum is just conserved. It doesn't change. Now, it's important to note that objects moving with a constant velocity also have angular momentum. So this is a point particle, right? And we use this when we're solving questions where we've got like a point particle colliding with something that rotates. And in the case of a point particle, we can actually calculate its angular momentum as well. And we could think of the equation for the angular momentum of a point particle as coming from this. So we've got this equation. The inertia of a point particle is mr squared. And then omega, right? I know that omega should be equal to v over r. Comes from this equation, right? Which I'll talk about in a minute. But then if we simplify, we end up with this result. And this basically says that the angular momentum of a point particle is just its linear momentum times its distance from the axis of rotation. Now, here's what an example might look like. So we've got some object with mass m that collides with a rod. The rod has inertia I, and then it sticks, and they both swing together with some angular velocity after they collide. So before the collision, the point particle has angular momentum equal to mv times L, right? Because L is the length of the rod, which is the distance from the axis of rotation to where that point particle is. And then after they collide, we can think of them as one object, right? Because they're stuck together. And the rotational inertia of this combined object is I, the inertia of the rod, plus the inertia of the point particle, which is ml squared. So this is the rotational inertia of the whole ball rod system. And this is the velocity of the system after the collision. So this would be a conservation of momentum equation for this system during this collision. Another important note is that we can use the impulse equation in the case of angular motion as well. So for linear motion, we had net force times time interval is equal to the change in linear momentum of an object. But this also works for rotating objects. So the net torque multiplied by the time over which that torque is applied gives us the change in angular momentum of an object. Now, last thing, or close to last, is rotational kinetic energy. And we looked at this in the main sort of example that we looked at this was for rolling objects. So if you have an object rolling down an incline, if it's rolling, some of its initial potential energy is actually going to be converted into rotational kinetic energy. It's not all going to be translational. So in the case of an object rolling down an incline, if you were to use conservation of energy to study what's happening, your equation would have to look something like this. Right? The potential energy is turning into a combination of translational kinetic energy and rotational kinetic energy. Now lastly, rolling without slipping and pulleys. Well, we had some important relationships we used to relate the translational motion of objects to rotational motion of objects. And they work in the case of both an object that's rolling without sliding, right? So it's rolling, but there's no slipping happening. Or if you have an object that's connected to a pulley, right? And you have that pulley that's like unwinding, you can use these equations, and in this case, this would be the displacement of the center of mass of the object, and this is the angular displacement. This is the velocity of the center of mass of the object, and this is its angular velocity. This is acceleration of the center of mass of the object, and this is angular acceleration. In the case of the pulley itself would be fixed, but all of these would be referring to the translational motion of this attached object as it falls. And I think that's about it. Thanks, guys. I hope this was helpful for you.